Hello, good afternoon. I welcome you all for the webinar, Your Eyes Beneath the Surface. We will wait a couple of minutes so people can join the webinar. I already like to let you know that you can leave questions in the chat or in the Q&A. If you have a question you want to ask yourself, you can also raise your hand, and during the webinar we will provide some time to go over the questions or start up a discussion. So please feel free. Good afternoon, you all. Thank you for joining. We will wait another 2 minutes so people are still joining the webinar. As also mentioned in the chat, you can leave your questions in the chat or in the section Q&A. You can also raise your hand. For now, you're muted, but while it's time for answering the questions, we can get the noise on and you can pose a question yourself. 1 minute, I wait 1 minute and then we will start the presentation. Hello, good afternoon. I'm Marianne Joris from iFlux, and I will present, and I hope we will also discuss how groundwater and mass flux improves the evaluation of contamination and the risks related to it and your remediation approach. Let me also thank Soilite, who is organizing this webinar. Soilite is a network of European companies who join forces to promote and to explain how new technologies can improve investigation and remediation of soil and groundwater contamination. So I'm Marianne, working for iFlux. And who is iFlux? iFlux is a spin-off company of the University of Antwerp and Vito, which is a Flemish research institute. iFlux, we focus on groundwater monitoring and to enable a data-driven groundwater management. We want to preserve freshwater resource, and we are convinced that with better knowing how groundwater behaves, we can better control and better manage groundwater resources. We have our own unique technology, the iFlux passive sampler, measuring groundwater and mass flux, and the real-time iFlux flow sensor, measuring continuously groundwater flow velocity and direction, and these data are available in real time, but I will explain that later on more in detail. So with iFlux, you can see the team here on the right in the picture, and it's a team which is passionate and driven by groundwater, and it's a team of hydrogeologists, remediation experts, but also experts in sensor technology, data transmission, and IT. We have been doing over 250 commercial groundwater projects, and we are still investing in research and development. As well, the commercial project as the R&D, we collaborate with different partners, consultants, but also universities and research institutes. We are already working internationally in Europe, but we are focusing on internationalization and collaboration with different partners all over the world. And yeah. So as I already said, we collect data for an evidence-based groundwater management, and we focus on groundwater monitoring, how groundwater flows, but also how it changes over place and in time. Therefore, we provide a sensing solution, which are monitoring networks with our flux sensors, and these have data available in real time, measuring groundwater dynamics. And also the iFlux samplers will, where we measure groundwater and mass flux for better investigation of the contaminated groundwater and to provide effective remedial approaches. For this webinar, first focus will be on the iFlux samplers and how it's used in the evaluation of contamination and remediation, but I will also explain some sensing solutions and what the added value is. What is mass flux? Mass flux is the amount of contamination that is moving through a certain area in a certain time. So if you have a surface perpendicular to the groundwater flow and you measure all these different mass fluxes, then you have the total mass discharge, so the total amount of contamination that is moving. There is a US document, the ITRC document, where it's explained how mass flux is used in the evaluation of contamination and remediation. And here you can find the link to that online information. How do we measure groundwater and mass flux? And therefore we use the iFlux samplers. Here you see some pictures of the samplers itself, and actually it are cartridges that you can combine at the preferable depth, and you can install immediately in wells which are available on site. There are different types of cartridges. There is one cartridge for measuring groundwater flux. It's filled with an active carbon saturated with tracer alcohols, and the tracer alcohols elute while groundwater is flowing through. Then there are other types of cartridges filled with resins who absorb contaminants or other compounds while groundwater is flowing through the cartridge. These cartridges are installed in wells. They stay there for a couple of weeks to a couple of months. and then they are retrieved and sent to the lab. The lab will analyze the tracer alcohols for the water flux and the contaminants adsorbed to the resin for the mass fluxes, and these are reported and calculated to mass flux. Here you can see the different components which are validated for the cartridges. Validation is performed by our partner SGS. As you can see, the different colors are different type of mass flux or groundwater flux measured. Blue groundwater flux, the red ones all organics, gray metals, nutrients and dioxane. And we have another page for the PFAS components, the package. And these components are all validated for the cartridge. That means that adsorption, desorption tests are performed and results are reported quantitative. More components can be analyzed by SGS if the standards are available in the lab, but without additional testing, reporting will only be indicative because we do not have information then about the adsorption and desorption capacity on the cartridges and for the cartridges. Additional testing can be performed on demand and in collaboration with SGS. So, as you can see, the measurements we perform are performed on site. They are local measurements, so it's very important to choose where you will install the cartridges. And therefore, we suggest or we advise to evaluate the available and missing information. This will that you have available. That will also help to get the objectives of your monitoring campaign clear, to define measuring locations and the detail of the research or the investigation you want to do. And it will also help you to determine the frequency of the measuring campaigns as well as the duration of the monitoring. So as you can see, what we need up front or what we ask you to evaluate is like, what do you already know about the contamination? How is it? What do you know already about the geology or hydrogeology? About the site-specific information, is there infrastructure present on site or other things that can influence the contamination and the spreading of the contamination in the groundwater? You can see some bore logs where geology is present, some soil probing, if you can see how permeable soil is, information about the contamination, analytical results, but also MIP or NISAS, that shows the distribution of the contamination in the soil and the groundwater, isohypsa, where groundwater flow direction or groundwater flow velocity is already more or less known, as well as the contour of the contamination, and here the geology as well on the pictures. So with the iFlux cartridges, we can't measure everything, or we can't answer all questions, but what we can answer is like how much contamination is moving, and is it a risk to the downstream receptors? Is the contamination moving by certain pathways, preferential pathways, and where are they located? And it will also help to better understand the dynamics. Are there variations or changes on site, but also in time? And this information will help to improve your design and follow-up of your remedial actions. Where the cartridges are less suited for is for measuring in zones with free phase, like D-NAPL or L-NAPL, or in fractured bedrock, where contamination is moving by fractures, because we are measuring in wells, and typically for drilling is that it will disturb the original the original state of the geology and influence the flow patterns. So, as I already said, it's very important to define what you want to measure and where you want to measure. And also, of course, how long the monitoring campaign will stay in place, as well as maybe it's needed to have several monitoring campaigns during different periods, for example. If you don't have any information up front, then the only solution is to measure everywhere at different locations, in a raster, for example, at different depth, different location, to have any idea about mass flux and mass discharge. But of course, most of the time already information is available, and it will definitely help to set up a monitoring plan to evaluate this available information. For example, you can already select to measure in near the locations of the contamination, downstream from the contamination, etc. Also, if you set up a monitoring campaign, it is the first thing you do is to define your objectives and to find out what the detail of the monitoring campaign is that you want to set up. If the objective is to evaluate spreading and to have only a first worst case estimation, it will be enough to measure in the area with high concentration and high groundwater fluxes. Of course, if you need more detail and you want to have a more average evaluation of the contamination present and spreading, then you will have to measure at more depth in the different layers, for example, in high and low concentration areas. Let me show this with this example at the right, for example. Here we had an industrial site. It was located over here. And there was source zone expected in this area. To evaluate the spreading of the contamination, wells or high flux samplers are installed in wells downstream at different transects, perpendicular to the flow direction, and one transect parallel to the flow direction. The transects perpendicular to the flow direction give an idea about the distribution of the contamination at different distances from the source. So if you measure with the flow direction, parallel to the flow direction, you can see how the contamination is evolving downstream in time, for example. For the year, we have chosen to measure at different depth in the two different aquifers and the two different soil layers. We measured in the shallow soil layer, which you can see over here, at two different depths, as well in the deeper soil layer, as well in the different wells at two different depths. That was the selection of the wells as well as the depths was done based on the HPC drilling performed before the iFlux campaign. And here we could see that the upper layer was less permeable as the deeper layer, but concentrations in this layer were higher. That's why it was chosen to measure in both one to better understand the mass discharge and the spreading of the contamination in both layers, for example. Also important to understand is that site-specific, for example, infrastructure or activities on site can influence the spreading of the contamination. As you can see over here in the picture, there is some concrete in the soil, which act as a barrier and where groundwater will flow around, but also contamination, which will influence the spreading of the contamination, which is very logical, but not always known. What we can see over here is that if we would do concentration measurements just upstream from this concrete barrier, concentration could be high just because of accumulation of the contamination upstream from this barrier, although the spreading is not going through. the spreading will, the groundwater will find its way around or underneath, and contamination will follow the groundwater flow. At the right, you see one of the projects as an example. Generally, the groundwater flow is flowing to the south, but there is a dike built over here which inhibits the flow of the groundwater. We see the groundwater fluxes just upstream from the dike and downstream from the dike. Mostly the groundwater flow downstream from the dike is very low, except for this location. The same we do see in the mass fluxes, where we see a very low mass flux downstream from the dike, except for this location. Also upstream from the dike, we see a mass flux. As you can see over here, it's a contamination that is moving, and the dike is stopping the spreading of the contamination, except for here. Here there must be some leaking, or there is some fit in the dike where the contamination and the groundwater can flow through. It can be a problem, but it also can be an opportunity for a remedial approach. And you know, if you have this information, you know where you have to take action and to improve groundwater quality, for example. Other things that can influence the spreading of contamination, of course, it's your hydrogeology. And then you often do not only have to look to your site yourself, but you have to also look a little bit further away. And it can be the natural hydrogeology, for example, nearby rivers or lakes that will influence the groundwater flow. These can, for example, a river upstream which infiltrates, but it can also be that the river drain the area and the groundwater will flow to the other direction, for example. It's not only natural things that can influence the groundwater flow, but it can also be activities, pumping activities, or redevelopment of a site that can influence the hydrogeology, and by this also the spreading of the contamination. As I can show you over here, one of the cases we have been measuring it was an industrial site with a historical contamination, and near that site a river was present. The river there was a lot of sediment in the river, which resulted in a very low flow in the direction of the river. Now there was risk for flooding, so the river had to be dredged, and therefore flux measurements are performed in the riverbed as well in the banks of the river to measure the fluxes from the industrial site to the river. After the dredging, measurements are performed in the riverbed, and as you can see, it are vertical fluxes that we have measured over here. Here you can see the groundwater flux and the mass fluxes. As you can see, there's a large variation in the groundwater fluxes, the vertical fluxes in the riverbed, depending on the size of the river, the depth, etc. So there's a large variation, but also mass fluxes vary a lot. Here we can see water flux is higher, but the mass flux to the south is even more higher because of the presence of different source zone. In the banks of the river, there were some wells available, and we did measurements before and after the dredging, and we can immediately see that the mass flux before the dredging was much lower than after the dredging. So indeed, the dredging of the riverbed had the result that more contamination, the drainage capacity of the river was restored, and more contamination from the banks, from the historical contamination at the industrial site, was flowing to the river with the risk of contaminating the surface water. Okay, with the help of this result, it was possible to design and to implement remediation measurements. So a permeable barrier mat was installed at the bottom of the river to prevent further spreading from the banks to the surface water. If you want to set up a monitoring campaign, you will have to evaluate if you can use the wells on site or new wells are needed. Of course, then it's important to check at which location and depth the wells are available, and that are the depth and location you want to measure. Does it answer the questions and does it answer the objective of your monitoring campaign? Of course, we need good wells to measure in. They have to be in a good shape. And testing can be performed upfront by pumping to see if water is flowing in regularly. Camera inspection can help, and we can also provide you with dummy samplers to test if there are no obstructions in the well, and the samplers can be installed decently. It is very important for us to know upfront the diameter of the well, because we adjust the cartridges, the diameter of the cartridges to the diameter of your well. Therefore, before upfront the monitoring campaign, we do ask information about the wells and about the site to prepare the monitoring campaign. Here you can see a template that we use to ask and to collect all necessary information. What do we need from you? We need first information of the wells, like, as I already said, the internal diameter of the well, but we also ask the outside diameter, the location of the filter screen, as well as the groundwater level, because we prepare everything up front. Not only the diameter of the cartridge, but also the length of the cable, so we can send you the combination of cartridges and installation equipment, and it's very easy to you to install everything on site. What else do we need? We also need information about the permeability of the soil and the filter grind, as well as the borehole diameter and the well diameter. This information we use to correct for flow field distortion. It's not needed upfront, but this information will help us to deliver accurate results, and also the possibility to compare results in different types of wells on site. Let me explain that a little bit more in detail. So if a borehole is drilled on site, this will already influence the flow in the underground. You have a borehole, you install a well, and if your gravel pack is, the permeability of the gravel pack is higher as the permeability of the aquifer, the groundwater will prefer to flow through the more permeable package, the filter pack, for example. So this will already influence your measurements. And therefore, we correct. So based on the information of the aquifer, the diameter of the borehole, the used filter pack, and our samplers, we correct for this flow field distortion. You can find more detailed information and testing in the article of Goede Leverheid, who is the inventor of this technology and also founder of iFlux. The testing is performed as well in the lab as with CFD modeling, and field experiences are combined to better understand the influence of this different type of wells where we do measure fluxes in. So here you can see, for example, the plots of the functional relationship of the alpha, the correction factor, with the hydraulic conductivity of the filter screen, the filter pack, and the different radii of the borehole and the well. And if for the most accurate measurement, it will be the best to have a correction factor close to 1, of course. But of course, we do correct so you can compare results in different type of wells. You can compare the result in different type of wells, and this will also help to see like which well are best suited for a typical situation of a typical site if you want to provide new wells. It's not all about flux. It's also very important that you combine the available data of different technologies to better understand how groundwater and contamination is spreading, for example. To characterize preferential pathways, we often combine iFlux campaign with geological and geotechnical information with HPT, CPT, or Waterloo measurements, the hydrogeological studies, and of course, all bar logs that are available on the location where you're measuring. MIP results to have a good idea about the distribution of the contamination, and MIP or NISA, and of course, the available concentration measurements over time do already provide a lot of information to choose where to measure fluxes and to better understand the spreading of the contamination. So also, iFlux measurements are also often used to validate groundwater and transport models. And then this information is combined with geological profiling, slug testing, hydraulic connection test, if there are several different layers available, present, volumes of surface water and concentration in ground and surface water, and real-time sensor networks. And this will bring us to the next topic, the real-time groundwater sensor networks. But maybe let me first see if there are already some questions in the chat, or if you already have questions for me. Sorry, I have to look in the chat now. Okay. I received a question in the Q&A. Do you have experience working with oil and gas companies? Please explain in brief these projects. Good questions. Yeah, yes, we do have experience with working with oil and gas companies. Flux measurements are performed in the investigation of their contaminations and to better evaluate the spreading risk or the spreading of the contamination and the design of these remediations. Maybe Jasper, I'm not sure if you want to explain a little bit more your question, because I think it's more as like I do not exactly know what you mean. I'm not sure. Jasper, can you see who had the question, or can we ask more explanation for the question?
It was not me who asked the question, but it was an anonymous.
It was an anonymous, indeed.
Okay, sorry. Yes, we do. Maybe, yeah, we do work for companies, and of course, it's an evaluation of their contamination. Yes, I think that's an answer on the question. Please don't hesitate. If you need more info, just let me know, and I try to explain better. Are there other questions in the chat or in the, because I cannot see it very well? I think that's all. So.
No other questions up till now, Marianne.
Okay, perfect. Thank you very much. Then I will go further with the presentation.
Oh, sorry, there's one coming in right now. What is the maximum depth you can go?
Yeah, for the passive flux meters, of course, it's an installation in a well, but we did measurements until 50 meters. We do implement additional calibration if we measure at larger depth. So if there is a water column from more than, for example, more than 10 meters, we do some additional testing, so see what is the influence of the installation and retrieval effect. especially for the groundwater cartridge, because the tracer alcohols, they will elute. It can be that they elute during installation. And if you go till a depth of 50 meters, it can be part of the tracer alcohols already eluted by installation. So we perform additional testing for that one, and we correct the results with the help of these testings. Another question in the Q&A I see now, if you used iFlux successfully in monitoring wells, in monitoring wells installed in low permeable fractured bedrock. We prefer not to do, I have to say. Indeed, fractured bedrock, it's not an ideal soil for measuring with iFlux samplers, because the flow will be dominated by the fractures, and we will measure in existing wells, and if you drill a hole in the bedrock, there will be new preferable pathways initiated by the drilling works, for example. We did measure in fractured bedrock, but important then is to understand what you're measuring. So upfront, the iFlux campaign, then geophysical research of investigation was done to understand where the fracture were present, and the monitoring campaign existed out of many samplers, and it was not one result that was the most important, but it was less the average of the different samplers that helped to evaluate how much contamination in groundwater that was moving through this bedrock. I hope this answers your questions a little bit. And there are more questions coming in. I have to see here. Do you only trace contamination? How about remediation? We do measure contamination, but indeed we also follow up remediation, because a lot of remediation techniques have the objective to decrease risks and to decrease the spreading of the contamination. And then it's important you measure the flux instead of only concentration, because that will give you more information about the result and the effect of the remediation. So we do measure before and after remedial actions, for example. But of course, you always have to pay attention that and be careful that the action you have taken, if there is still some, for example, injection product present in the soil, that you have to evaluate, like, can this influence my measurement? For example, if you have some oxidant that you inject, it can influence the measurement of the water flux, for example, because the alcohols will be oxidized. And then you have to be careful with the interpretation of the results. So it's very important to take that into account by setting up the monitoring program. Another questions, are there limitations in terms of the minimum water flux that can be measured? Yes, there are limitations of the minimum water flux, of course. We measure in centimeter, in as low as a scale of centimeter a day, but it's a tracer test, so the most accurate results, flux results, are around 10 centimeters a day. We can measure lower fluxes, but always be careful with the accuracy of these measurements. We can measure as low as 1 centimeter a day, but the most accurate results are around 10 centimeters a day, or a little bit lower. Okay, thank you for these questions. I hope the answers helped you further and meet your demand. And then we can go further with the presentation. Of course, there will be more time for questions at the end of the presentation, so don't hesitate to put them in the chat or the Q&A. I have to look for my presentation on my screen. Sorry for that one. So the real-time groundwater sensor networks, these are networks that are set up with semi-continuous measurements where we measure groundwater flow with the iFlux sensor, where we can measure vertical and horizontal flows. But these sensor measurements we combine with other quality sensors or available level sensors in the market, but also other water data. So we will also can follow up the weather and surface water to better understand the complete water system, for example. The data of this groundwater sensor network is transmitted and available in a dashboard and in real time. So, of course, depending on the needs and the frequency of the measurements, for example, we can measure every hour and send it every hour, but we can also choose to measure every hour and send it only twice a day. So then it's near real time, I would say, that data are available. And these choices, we make these choices based on the battery capacity and of course also the objective of the monitoring campaign. Let me explain a little bit more about our real-time flow sensors. The measuring principle, we measure with a microfluid flow chip, which is built in a sensor probe. Here you can see the probe measuring vertical fluxes, where there is an in and an outlet, or vice versa, depending if the water is draining, exfiltrating, or infiltrating. In the horizontal probe, we build in two microfluid flow chips, and based on the vector sum, the flow through these two sensor chips, the flow direction and flow velocity is determined. We do not make the microfluid flow chips ourselves. These are chips that are used also in the medical world. But what is the expertise of iFlux? It's also the conversion of the measured flux, the measured velocity in those fluid flow chips to the flux in the aquifer. And therefore, lab testing is performed and also testing in our digital lab, where the correction of the effects of wells and filter packs are calculated. Digital sensor, we do measure continuously, and this sensor is a more accurate measurement as the iFlux sampler, and therefore we have chosen to only install them in a pre-pack filter that you can see over here. So, and that means that these windows that of the filter pack are also, you can also find back the filter, the windows you can see over here of the sensor. They're the same windows you can find back in the pre-pack filter in the filter screen. So flow is can enter freely and regular in these small sensor where we are measuring in. So I have another case. I have a case where we set up a monitoring network. Sorry, I have to drink. It is a drinking water company at the Dutch coast. And here fresh water is infiltrated in ponds on site, as you can see over here. Fresh water from the River Meuse. And it's extracted as drinking water by different pumps in between these infiltration lakes. As protection of climate change, a sand motor is built. It's here front of the coast, like sand is installed. But what we saw is that with the installation of the sand motor, there was the risk of salt water intrusion was increasing. And beside that, there was also kind of a landfill present, as you can see over here, in the dunes where there was a possibility that contamination was present. And also with the installation of the sand motor, the hydrogeology inland changed and there was a need for better monitoring of the groundwater flow on site. So beside the monitoring, also protection wells are installed just over here near the coastline to ensure that no salt water was extracted by the drinking water supply, and also to control the water present near the landfill. So no contamination or salt water would intrude the drinking water wells. Here you see a different picture. You can see from the air the different protection wells near the coastline. The blue dots are the wells for drinking water supply, and in between you can see the ponds where water is infiltrated. So here you can see the ideal case. This one are the extraction wells for the drinking water supply. Here you can see the ponds where fresh water is infiltrated, and here the protection wells to protect the drinking water supply from saltwater intrusion, but also from the contamination moving to the drinking water supply. So to follow this up, different flow sensors are installed between the protection wells and the drinking water supply. And in the ideal case, the watershed is over here. So in sensor 2, there is a low flow, and maybe it can change a little bit from left to the right. But the water at this, the sensor at this shows that groundwater is flowing to the extraction, and at this area, the groundwater is flowing to the protection wells. Sorry, I have problems with my mouse. In the less ideal case, the protection well are over-extracting, and fresh water is pumped by the protection wells, and water is getting lost, which is not the objective, of course. But even worse, and what the drinking water company absolutely doesn't want, is that salt water is intruding the freshwater supply, neither as the contamination. So therefore, groundwater, the groundwater is controlled. So here you can see a map with the different flow sensors. We have different transects where flow sensors are installed at different distances between the protection wells and the drinking water supply. This was in total 15 flux and pressure sensors are installed, 2 conductivity sensors to follow up salinity, and in 4 locations there are installed level sensors around the flux sensors to validate the measurements in these zones. In the middle distance between the protection well and the drinking water, flow sensors are installed at 2 different depths, one shallow one around 5 meters and one deeper one at the maximum depth of 18 meters below ground level. So here we see some pictures of the installation of the flow sensor, the pre-pack filter, and here, especially for the deeper wells, sonic drilling is used to install this one. And here you can see the installation of the sensor with the data transmitter finalized or finished in the protection cap. Here again, you see the different transects where we are measuring. And let me first dive a little bit deeper, show you the measurements in the flow sensors at this location compared with the level sensors just in the immediate area of these flow sensors. And as we can see, the flow direction over here, here you can see the flow direction measured with the flow sensors as well as with the level sensors. And we can see that it's all very accurately. Only in transect 3, we do see a little difference of 10 degrees in between the measurement with the flow sensor and in yellow, and with the flow sensor in blue, and with the level sensors in yellow. If we focus on Transact 1, we see that the level sensor closest to the drinking water supply, the groundwater flow is flowing to the south. More in the middle, in the undeep flow sensor, groundwater is flowing to the northwest. And in the deeper one, it's more to southwest. And in the north, the one closer to the protection wells, groundwater is flowing to the coast, to the northwest. If we visualize these data or these flow measurements on this heat chart, here we combine the direction, which is, you can see here in degrees, with the velocity. This closer to the center is a slower flow velocity, and further away is a higher flow velocities. We can see that indeed the colors are the same. Here groundwater is flowing to the southeast, and in the central wall, where we can see direction is changing. It is changing, but flow is very low. So even when it's changing, we can see we are measuring very close to the watershed, or exactly on the watershed, which means that here we can see that direction is changes, but the influence is it's nothing, just because flow is that low. And that's what we can also see in this graph, where groundwater flow is very low in these two sensors, and higher in the sensor closer to the protection and the groundwater in the drinking water supply. Here we see different rabbit ears, I would say. So we see an increase of the groundwater flux, and that's the immediately result of stopping of the groundwater pumping in the protection wells. Let's focus a bit more on the first rabbit ears, I would say, and we can see that when pumping in the protection wells was stopped, we immediately see the effect in the groundwater flow measurement, as well as in the level measurements closest to this protection well. We see also an effect in the wells, in the measurements near the watershed, as well in the groundwater fluxes as in the water levels. Sorry, yeah. The second we see there, it was only one pump that stopped pumping, and there we can see that the groundwater flux measurement is a little bit more sensitive. We can see the effect in the wells close to the protection wells, and also in this one to the watershed, while the water levels, we don't see any effect anymore in the wells near the watershed. In Transact 3, we see something different. We see that the well closest to the drinking water supply is not flowing to the southeast, but more to the southwest. Centrally, near the watershed, water is flowing to the south and southeast. And in the well closest to the production well, water is flowing to the northwest. Here you see them as well on the heat map, and the different results over here. We also see here in the green one that we can very clearly see the influence of the pumping in these groundwater flux measurements. Can we explain this strange direction? Because we would expect that groundwater would flow to the drinking water supply. Yes, we can. As you can see, the pumping wells here and here located. Probably this location of the well is just on the watershed in between those two pumping areas. So the water here, some fresh water is leaking out this area, and action can be taken to prevent outflow of fresh water from the area. Another thing we see in Transact 3 is that water is more flowing to the west as expected. And we did find some reasons for that one. As you can see, the pumping well, the activity of pumping well BR21 is much more lower as in BR22. So this pump was less active, which explains the direction of this groundwater flow. So with this, we did set up several networks, and this is one example that made it possible to validate the flux sensors. We saw that the effect of the drainage of the protection wells was further inland than expected, and that real-time watershed monitoring based on flux measurement is possible and even more sensitive than if we would only do it with level sensors. We do expect more variation, seasonal variation, or effect from extreme weather events, etc. So the monitoring will be continuing, and the integration of the client data is essential. So it's not only groundwater you need to measure, but also you have to collect the pumping data to understand what is going on, and of course to use this data to take action. So for this site and also for other sites where we're measuring on, we continue with data validation and model integration. So thank you for your attention, and I was wondering if there are still more questions. Let's try to go to the chat. Please, you can also raise your hand if you have questions, and then we can go for discussion if you like. Go. What is the operating life of the real-time sensor? Good questions. Actually, we do not sell the sensors, but we provide you with the data and also the maintenance of the sensor. So you will only pay for the data and not for the sensor. So if the sensor, we will replace the sensors if you need the data for a long term. So we will replace them in time, for example. I hope that answers your questions. What is the operating life of the real-time sensor? Okay, that's the same one. And I think there are the questions in the chat and maybe more in the Q&A. No. Okay, if you have more questions, don't hesitate to contact me. I will be happy to help you further. Sorry, yeah, I thought there were more questions, but no, there aren't. Yes, leave a message and we can. I will contact you, or I will be happy to discuss. I will be happy to discuss with you what is the best your questions and remarks. Thank you very much.
Let's see, one more question. How long the Dunia project was going on, or what is the time frame of it? But I see most of us are leaving the room, but maybe one more you can.
Yes, that project is going on for 1 year. We do have in Poland, we do have a project that did start up, I think, in 2019, and there the sensor are still operating, of course, with the necessary maintenance in between. So yes, it also depends on site-specific circumstances, I would say. There are locations with very clean water, but also locations which are heavily contaminated, which definitely can influence the maintenance needs on site.
Okay, thanks to everybody. Thanks, Marianne, for the interesting presentation. We had a lot of people in the room, and as Marianne said, you find her details over here, of course, also through our Soilite website or directly iflux.be. Thank you very much, everyone. See you next time.
Thank you, Serge.